All right, let's get started here. It's 10 o'clock. Good morning. Thank you all for joining us. And I know there's going to be people that come as we're starting here, and then we're also going to be posting this webinar on our website in the future. So welcome to Interface Fluidics webinar on how to build a great microfluidic system for industrial fluid analysis. My name is Jason Innes, and I'm the director of Sapphire Lab here at Interface. And with me today is Tom DeHaas. Tom is a co-founder and CTO of the company. Morning, Tom. How are you doing?
Doing well, doing well. Excited to talk microfluidics this morning.
Good. Yeah, I know I like a lot of people watching today, and they'll be watching in the future. I'm looking forward to hearing your thoughts and your in-depth analysis from, 10 plus years of you working in the area of industrial microfluidics. And maybe just for the sake of everybody, I mean, the background here is the idea for this webinar and potentially a series of webinars in the future is that people always ask us questions about um, things we have conversations with customers and prospects and people who want to build their own systems and they want to understand how we've done it and what we do. And so that's why we're here. And people struggle with different, specific areas, whether it's pumps, microscopes, and so on. And what our goal is to get the conversation started here. We're probably not going to go into enough depth into each of the areas because there's so many areas. But what I'm asking anyone that's in the audience today is if you have questions as we're going, feel free to put them in the chat box at the bottom of the screen. We'll field your questions as Tom's talking. I'm just going to be the moderator here, and I have a lot of questions to ask Tom as well. And also, if you have ideas for future areas or webinars and specific topics that you'd like to see, feel free to suggest them in the chat. And we'll consider that or evaluate that for the future and to see how it fits. But yeah, we're really looking forward to it. So thank you for joining us. And just to go through, here's a little bit about our customers. So Interface Fluidics, we've been around for over 8 years. We're both a service company and a product company. And on the service side, we do lab testing in the industrial fluid analysis area for companies, as you can see here. So, Chevron, Select Chemistry, Exxon. We've got different companies around the world that also have our products. And there's also some universities and academic institutions that we've listed at the bottom there that we have been working with. So we're excited to have all of them as customers and definitely excited to have you joining us today. So, Tom, take it away.
Sure. So today we're going to be talking about a number of things. The first thing that I wanted to go through is to just give you a bit of the goal of this webinar. So um, Jason and I scoped this out to sort of be um, as applicable to as many different brands of equipment or types of providers, whether this is something where you're looking to get some extra information to design a system yourself, or if you want to go out into the market and find a product that could solve your needs, being able to identify what to look for in a full microfluidic system that's out on the market. We hope to help out both types of folks that are looking to enhance their laboratory capabilities.
Hey,
And
Tom,
so,
just
yep,
just can I ask you on that first one? So, and our intent here is we're not necessarily looking to recommend brands or breed. We're trying to be more brand agnostic here and not pick one over another. Is that true?
yeah, absolutely. So you'll notice in most of the slides I've added in more cartoons than exact photos of particular manufacturers' equipment to try to make it so that folks can focus on the feature set that they're looking for rather than going out and just buying a particular thing that we recommend from a microscope manufacturer, for example. Um, so the scope of what we're going to go through today, first of all, defining what we're actually talking about here. What is an industrial microfluidic system compared to um, other places where you might use microfluidics in the biomedical space or fundamental fluid analysis things. Going through some of the unique challenges of building these systems. For example, I started my journey in high pressure microfluidics at the University of Toronto like over a decade ago now, when we were trying to go from primarily plastic-based microfluidic systems to systems that can handle high pressure and more difficult to work with solvents. And we'll talk about the architecture of what are the core parts of a microfluidic system that you should be concerned about when you're out building something or looking to purchase something. And lastly, going through some tips on addressing the core problems in a high pressure system, like safety, flow rate control, live sample handling, materials compatibility, and data capture and data pipeline issues. So industrial microfluidic systems are a combination of two different fields. Industrial fluid measurement, which is been around for a long time, is very adept at running high temperatures, high pressures, corrosive fluids. These are a lot of standalone testing systems that are very well accepted in industry and provide good results, if not without their own limitations, slim tube and PVT cells and things like that. On the other side is the world of microfluidic measurements. Outside of the scope of industrial microfluidics, there's the whole world of biomedical microfluidics, which is gigantic and far larger than industrial systems. This will include like flow cytometry, drug discovery, gene sequencing. There's a whole bunch of very large companies doing these very successfully. The scope that we're focusing on, however, is the intersection of these industrial systems and microfluidic systems. And so this will cover micromodels, on-chip PVT measurements, on-chip MMP measurements, and microscale density viscosity measurements.
I would add, Tom, that just in the scope of things, I mean, the breadth of what you can test in that area goes beyond PVT, MMP, density, and viscosity. There's a whole bunch of other types of things that people can do.
Yeah, there's people that are working on material synthesis, for example, that might want really high temperatures, or other areas that they're looking at, fundamental droplet dynamics or jets of fluid or whatever. So some of the main areas that we've seen people interested in industrial microfluidic systems for is largely in the energy space. So for example, here in Alberta, there's lots of companies interested in thermal oil recovery, which is typically a lower pressure, higher temperature process. And then on the other side, there's lots of offshore oil and gas producers that are interested in live oil studies or onshore live oil studies. These tend to be very high pressures, but lower temperatures. Of course, these are all very gross generalizations of where things are, and sometimes people are operating outside these envelopes. To give a scope of where most of the microfluidic systems in the world live is down here in this dark blue box. The medical industry is not interested in how things work at 100 degrees Celsius because nothing in your body is at 100 degrees Celsius. And they just want to have things that work with living cells. So because the vast majority of the microfluidic world lives over in that little blue corner in the corner in biomedical land, this means that the vast majority of parts that are available on the market are for biomedical applications. And on the flip side, the industrial equipment is usually a much larger volume. And so you have this, the first challenge is that The industrial high pressure systems tend to not get small enough, and the biomedical systems tend to not work at high enough pressures. And so this presents a challenge of actually finding stuff that works at these conditions. This is just a picture of a gigantic valve that maybe you can find things smaller than this, but you know, finding valves that are as small as the what you need to use in a microfluidic system, there's fewer manufacturers that will do 1/16 inch valves, for example. The other challenges here is controlling flow rate at the microliter range. We're going to talk a lot about that, controlling live fluids, and then logging data from a large number of sensors. Because you're trying to control more in your system, there's more challenges with logging and assembling the data after the test so you can actually get results.
Actually, Tom, I just a few questions for you on that last slide. Can you give an example to the audience of like where you have a material fluid combination that's incompatible that people might not be aware of?
Yeah, that's a good question. So the first the whole reason that I started using hard materials like glass and glass chips and glass silicon chips back at the University of Toronto was that um, the common polymers that are used in microfluidic chips like PDMS and PMMA are completely incompatible with solvents like toluene and supercritical CO2. Those fluids will basically disintegrate or shatter those plastics, and you have no chance of running a test. You need to go to these more solvent-resistant materials in order to work with these fluids.
Thanks.
So this is a cartoon with super high level of the core pieces of a high pressure microfluidic system. So in the top left here, you have your data acquisition system. That's sort of the brain of the whole system. It's controlling your pumps, temperature controllers, your microscope, everything. The on the left here, we'll start here. This is usually you'll have a number of pumps doing the injection into the system. People will want more than one because typically you're trying to do an oil alternating with a gas or a oil water or brine and CO2. There's usually multiple fluids that you're trying to inject. So usually you want multiple injection pumps. There's a lot to be concerned about when selecting these, and we'll talk about that coming up. Live sample handling. On these ones, these cylinders are actually in here backwards, just notice that. But the hydraulic fluid will be on the pump side, and the process fluid will be on the chip holder side. For these cylinders, you sometimes will want to isolate the process fluid from the pumps because it can damage the pumps if it's, for example, oil that contains H2S. Most pumps can't handle that fluid. And then also live fluids. Sometimes you'll need to recombine them separate from the system and then bring them on. Pressure sensors, there's a lot to be concerned about with pressure sensors. And here at Interface, we went through a number of manufacturers of these before we sort of settled on what we do now. We'll talk about those. Chip holding, there's not a ton on the market outside of what we manufacture, but we'll talk about some of the things to be concerned about. Lots of the academic groups will manufacture their own chip holders. Microscopes, temperature control, we'll also be talking about.
Tom, actually, just a note. You indicated microscope here, but obviously there's a whole optics category that microscope is one of many things that you would have to consider. What are the other things that you would be concerned with here?
Yeah, so within that category, typically you'll have a light source, the actual microscope, a set of filters that you'll use depending on if it's fluorescence imaging or bright field, and a number of objectives depending on the magnification you're looking to get. And then you'll also need to select a camera that's appropriate for your application. So we're not going to go into super depth on all of those, more so just talking about the bigger picture for microscopes today, but there's a lot to dig into on selecting the correct product for your application there. Okay, so chip holders. Most people will start out over here in the low pressure world. This is one of the few PDMS chips that I ever made for the cover journal that we were working on. This is PDMS for those who don't know, is a soft rubber material that you can very simply fabricate any type of pattern into and make these devices for pennies. They're really good for running fluids at low pressures. But once you start going to any type of pressure or any type of harsh solvent, this system will start to literally fall apart, swell. Um, Gases will diffuse into this material more easily than into other liquids. You get all sorts of effects that you're not looking for. So people will quickly realize that PDMS is not a solution for high pressure testing. Once you enter the sort of medium world is where people will start to build their own chip holders, go out into the market, find products that will reach sort of into that 100, 200 bar, which is the 1500 PSI, 3000 PSI range. And these will sort of be in a medium price range. They still have the advantage of being able to change chips in and out quickly. So if you're running a test every day, you can use this type of system to quickly change out your chips. You'll notice that this is an example from what we manufacture, but the working distance, we'll talk about that. It's the distance between the end of the objective and the chip is smaller in this case, so you have a larger range of options for microscopes. And you can make these out of any type of material, so your compatibility is great. So you can run harsh fluids like supercritical CO2s, oils that contain H2S, all that type of stuff. And then once you enter the world of high pressure systems, usually you'll have to go to a system that involves liquid confinement. There's a few people that do low volume of making these systems. This is one that we make called our liquid confined chip holder. Liquid confinement basically surrounds the entire chip with usually a mineral oil at very high pressure. And what that will do is allow you to take the process fluid inside the chip to whatever pressure you want, as long as it's lower than the confining fluid. So these types of systems are great because you can have a lot of freedom to bring your chip up to whatever pressure you want. You also can design chips with much more open volume because you're not as dependent on the physical structure of the chip to hold the pressure.
Now, hey, just a question on this one. You kind of touched on it when you were talking about the medium pressure category, but obviously, there's a wide berth of like materials or fluids that people are using, um, and obviously the metal they were using here is pretty important to match with the fluids that people want to use. Can you talk a little bit about selecting metals, like if someone was to build their own or
Yeah, absolutely.
things that they would
We'll have
want to consider?
we'll have a slide further on about exactly that. But yeah, you're
Okay.
right. Is that the some of the materials like the lid and the base you can make out of whatever, but the parts that are wetted by process fluid, in this case the base of the chip holder, you're going to want to be considerate about which material you choose. So the next part here that we're going to talk about is your microscope. Um, the majority of microscopes that are on the market are built with sort of a cast C-shaped frame like this. Most people in the call here who own a microscope will probably either have an upright or inverted microscope that has a cast frame. Um, with a stage on it that will allow you to move the chip around. This is designed for biological applications largely and can present a bit of a challenge when you actually have larger metal chip holding that you have to put into that microscope, because your first concern will be the clearance to actually fit a chip holder into your microscope. So the screw top one that we have is a bit lower profile, so it might fit in some microscope systems. That larger one that we have, the liquid confined chip holder, would be very challenging. Or if you're designing something yourself, very challenging to fit a larger chip holder into a traditional microscope. The other concern is the working distance, which is largely a function of your objective. So the objective of the microscope, you can find a number of manufacturers. Most of them will have a great tool on their website where you can sort by working distance. For the most part, a high pressure system, you're going to be looking in sort of that 15 millimeter plus range, which is on the high end of working distance. You'll be unable to use things like oil immersion objectives and very high magnification objectives that usually demand very short working distances. And once you get all this put in and put together, if you have a pole mounted microscope, one thing that you should be concerned about is specimen tilt. This means that you want to make sure that the light coming from your microscope is completely perpendicular with your chip. If this isn't the case, you'll start seeing shadowing and other issues. So the two broad categories of microscope that people use with microfluidics, one is called epi-illumination. In this case, it means that you're illuminating through the objective and imaging the light that reflects off of your specimen. In lots of cases, people have microscopes that are set up for transmitted light, where you'll shine light through the specimen and into the microscope. You can build high pressure systems that allow for transmitted light microscopy, but it means that all of the big metal stuff like O-ring grooves, heating, all this stuff has to somehow fit on the outside of the chip. So they're both options. We've found as a company that epi-illuminated microscopes are much simpler to work with.
And Tom, that's all we use, right?
That's all that we use as a company, with the exception of our SAGD services, which are done with larger size glass microfluidic chips. So the next piece that you'll have to be aware of is which pump you're selecting. There's for folks on the call that are coming from the industrial side, you might have very large volume pumps on hand, say 200 milliliter, 400 milliliter pumps that go to 20,000 psi or something. These are fantastic for compressing gas and for being able to quickly get to the pressures that you need. However, they present real challenges with microfluidics because you cannot reach the lower flow rates that are needed. And in some cases, the number that's displayed can be quite wrong when you actually measure it. There's quite a lot of error sometimes on the low end. And lastly, one of the issues that we've seen with large syringe volumes is that if you have, say, 200 milliliters of fluid and your room temperature changes throughout the day, you can see artificial flow that comes through the lines. And so that if you set the flow rate to say 1 microliter per minute, your flow rate could actually be 3 microliters per minute or something if your room's heating up. Compact syringe pumps really eliminate a lot of those flow control problems, but present their own issues. So if you're running a small syringe pump, less than 10 mils, first off, there's far fewer manufacturers that make these at high pressures. There's a few. these will have more accurate flow rates just because this is a function of the diameter of the syringe and the speed that you can move the plunger through the syringe. These are can be very poor for handling gas because you'll have to cycle the pump a number of times if you're using a sample cylinder, for example, to compress a gas, which means that you'll be finding yourself refilling the pump frequently. And so as a company, we tend to balance the use of larger, say 10 milliliter syringes and smaller 3 milliliter syringes, depending on the application. And for some very low flow rate things, we'll go all the way down to like 500 microliter syringes. At that diameter, you get a lot of advantages that you can nail your flow rate perfectly, but it would take you, 50 cycles of your pump to just fill up a very large tubing string that you leads up to your pump. So it's not practical for some applications to use very small syringes.
Would we ever use like when in these categories, would we ever use the 50 mil pumps in one of our systems?
Um, we use large pumps for a couple of things. Is for handling live fluids, you still need to do sample preparation that's very similar to using a PVT cell or a slim tube. You'll have to subsample off of a sample bomb that you get, which is usually 500 milliliters or larger, and then put it into one of the smaller bottles that we'll show you that we use on our systems. And that process, it's more convenient to use a big pump for that. And then also, especially for very exotic gas mixtures that have a lot of heavy ends, you'll find that a large syringe is great for compressing that fluid. And sometimes you'll need to cycle the pump a lot. So using a 200 milliliter syringe or something to compress gas from 5, 10 psi up to thousands of psi, it's definitely the way to go. So typically we'll
And
use those large syringes in like a supporting function more so than running directly into our
in
system.
this, and can you give people a little bit of an indication on when you're looking at compact syringe pumps, like what type of things are you looking for if when you're choosing a pump? Like what are the other variables and factors that specifications that you would look for when choosing a pump that's suitable?
So the biggest one is usually reliability, in that if you're going to be using this every day on something that's hooked up to samples that are in the thousands of psi, you want something that's going to work every day and not fail on you. So finding something that's um, more reliable is usually a good option. You want to look at the if you want to control it with software, looking into the software development kits that are available for each pump is a good idea. And some of these pumps, another big difference is that very few compact syringe pumps allow for pressure control. Usually you'll have to either add an external pressure sensor or something. They'll all give you flow control, so you can set up uh, a flow rate. But if you want to set a constant pressure, typically they won't include a pressure sensor. So you sort of have to make something yourself. And that's what we've done through our software.
And are most of the pumps that are available on the compact side, are they as durable when it comes to withstanding like the syringe being able to withstand different types of fluids, or are some better than others?
Um, the syringes, they they'll you can buy them in a number of different materials. So the big thing to be aware of is just to select a syringe that's compatible with your fluids. Lots of these syringes are made out of 316 stainless steel, so if you fill them up with really heavy brines and leave them, they're going to rust on you. Um, so you just have to always be aware of treating your equipment properly, not spilling brine all over it and leaving it there. Um, so it depends. If you're going to be using it every once in a while, you can go for a cheaper option. If you want to be using this day in, day out, going for a more industrial, more precise system is better.
Okay.
The last two I'll just quickly mention is on the market you can also get peristaltic pumps. These operate by putting a roller against flexible tubing and pushing pulses of fluids. These are not great because you'll get pulses of fluids going into your chip and it'll largely damage your results. And there's also pressure-driven flow control, which is available for low pressures. These can be really nice for things under about 5 bar. Or under 100 psi. But if you're at higher pressures, these aren't great. Pressure sensors. The pressure sensor is one part of the system that we probably had the most trouble with as a company over the last 8 years or so. On the market, the vast majority of pressure sensors are designed for process systems that have large volumes, and you'll find on the market most of them will have a 1/4 inch NPT thread connection. And in order to adapt this to tubing, you're going to need to add a bunch of your own stuff. You'll need to add like a union and a T and some tubing, and all this adds dead volume to your system. It can make your results have incorrect pressure readings. This dead volume can contain fluid from your previous test and contaminate your next test. And sometimes if you put gas in there and you have liquid in your process line, it'll sort of add a damping effect to your pressure reading. It's not great. There's a whole bunch of reasons that we stopped doing this.
But actually, when you're
Yep.
cleaning the system, wouldn't the cleaning get the old fluids out of the dead volume area?
It will if you remove the pressure sensor and like squirt solvent inside of it and clean it out that way. Um, that's definitely possible. We used to do that, but it just adds a lot of time to your testing if you have to remove your pressure sensors every test. So now what we've done is found inline sensors. There's a lot of manufacturers that make these on the biological low pressure side and fewer at the higher pressures, but they do exist. And the nice thing about these is that you can do inline cleaning. So you can run your test, you can flush some solvent, be assured that you don't have any oil or other chemical left inside the sensor. And because you don't have this line leading to your sensor, you'll have lower error. You won't have as much latency. So many advantages. So I recommend these inline sensors. They're great. Once if you're looking for these types of things, you might find that you'll see analog and digital sensors. The analog ones will give you like 5 to 20 milliamp output. The digital ones will have a USB connection or some sort of other connection. The advantage of digital is that you can save the calibration directly onto the device, and you know that every time you connect, you're gonna automatically have your slope and offset put into the numbers you see. There's also a couple other things to be aware of as you want to match the sensors, the full scale range of the sensor to your application, knowing if you have a 20,000 PSI process, you're going to use a 20,000 PSI sensor. And if you have a 5 PSI process, you use that 20,000 PSI sensor. It's not going to hurt the sensor at all, but your results are probably going to be pretty inaccurate because usually the pressure sensor readout is a function of the full scale of the sensor. So be aware that you want to match the sensor to the application. Also, you can find sometimes that you'll get a lot of resolution on some sensors. They'll give you like 3 decimal places of precision, but that 3 decimal places might still be, 100 psi off from what your actual pressure is. So you want to look at both the accuracy and precision of the device.
Because you mentioned it on that one, I wanted to just ask you a question about dead volume when you were talking about sensors. What are the other system components that people would have to be concerned about or that are part of an industrial microfluidic system that really contribute to dead volume that people should focus on?
Yeah, so the valve selection is important. Some valves, like ball valves, will contain a lot of volume. Um, the pumps will have a lot of volume. There's both, to be more specific, the dead volume of volume that's not in the process line is usually mainly pressure sensors, but the total system volume that can be impacted by your pump selection. If you choose to use sample bottles like these, it'll also increase your system volume a lot. And also the amount of tubing and the complexity of your valving setup. The more capable you want your system to be, usually you put more and more valves in, and that will add system volume.
And why is system volume bad?
Because when you fill up your syringe pump with fluid and you want to get it from your syringe pump into your chip, you have to push fluid all the way through all the tubing and valves to get it into your chip. And if you have a 3 milliliter syringe and 5 milliliters of piping between your syringe and your chip, you're going to have to cycle your pump 2 times just to fill up that volume. And so uh, that's usually the main concern around system volume. Also, this temperature issue of if the room temperature changes, it can induce artificial flow onto your chip.
And does system volume affect your flow rates within the chip or the measurements or the data that you're getting out through the images at all?
It will, because you might still get good pictures, but your data will be wrong because you'll think your flow rate is one thing, but it's actually different. So it can impact your results, and we've seen that, and we'll talk about how we've mitigated that with our system. So the next part is live sample handling. Adding sample bottles to your system is something that I'd recommend against unless you have to, because it presents additional challenges. It'll make your system more complicated, but lots of the time you just can't get around it. If you're running live oil samples, pretty much have to use some sort of a sample bottle. The reason being is that you're going to want to have the ability to constitute your sample. If you subsample off of a big bottle, you'll need to rock the sample back and forth with a mixing ring in there in order to homogenize the sample before testing. And you can't do that in a syringe. You have to do it in a sample bottle. So we also use these for gases because it's more convenient to compress a large volume and then run a number of tests.
Okay, actually, just hold on. You just recommended to people not to include this, but most of our systems we always use these, and we
Yeah,
use these all the time in the lab. So is it just because, like you said, we use live fluids all the time, we use gases all the time,
yeah,
we use corrosive materials, we use expensive pumps, so we don't want to wreck the syringes that come with them. Are
yeah,
those the reasons? Like
yeah,
it would be, you're
absolutely.
saying it'd be ideal if we didn't use these.
Yeah, everything that we talk about in this presentation has trade-offs. And that's sort of one take-home message, is that there's not one instrument that you can purchase that's perfect for everything. You can always find a better microscope or a better pump for if you just are looking at flow rate control or resolution or something like that. But there's usually a trade-off. If you're taking all of your images at 100 megapixels, you're going to crash your computer because you fill up your hard drive. There's always benefits and drawbacks. And what we've found is that for working with live oil samples and working with gases and working with corrosive materials like sour oil samples, you're going to want to use a sample bottle because it isolates your pumps from your system and it lets you have larger volumes to run a number of tests if it's inconvenient to reload the the bottle from the main sample bomb that you're given.
So you're saying that they're necessary, but they add a lot of complexity as well and cost
Yeah,
possibly to a system.
absolutely. Yeah, and you also have a challenge that you can get lower precision on your flow rates because the seals within these bottles can stick and slip, no matter which manufacturers of bottles you're using. The O-rings can tend to grab onto the material, and um, slow down or change the flow rate.
Which is obviously very important when you're talking nanoliters of fluid.
Yeah, absolutely. So you would want to run directly from your pumps if you're running very low precision flow rates um, without live fluids. So the next thing here is temperature control. There's a number of things to be aware of, again, with the accuracy, precision, and safety. So in the accuracy side, you want to consider the offset between your sensor reading and the on-chip temperature. This is important because even though your temperature readout might be 50 degrees, what you see on the chip, it might be 55 or 52 or 40 or something. You want to make sure that you're aware for this. And when we sell chip holder systems, we include an offset for this, especially on the screw top one that has more of a temperature offset between the chip and the um, set point. The temperature uniformity piece is important, both on chip, knowing that your temperature is consistent across the whole chip, and if you're doing heating of your valves, your lines, your sample bottles, you want to make sure that maybe uniformity is not as important as on chip, but you don't want one part at 100 degrees Celsius and another part at 20 if you think it's a lot of 100. The precision piece, this will come down to your controller, your sensor, and your heater position. If you have infinite money, you can buy very, very expensive controllers that will hit 3 decimal places on your temperature precision, but you might not care about that. So you want to make sure that you choose a controller for each application that is within your budget and within what your process demands. So some parts of your system might require lower precision than others. In our case, we'll use higher precision controllers for the chip holders. The safety aspect is also important as you get up to higher temperatures. So consider adding thermal limiting switches or fuses or GFCI breakers as appropriate. I've seen some pretty sketchy temperature control visiting various universities around the world, and so just be sure that you do this safely. So the challenges of high pressure microfluidics. First off is safety. So unlike running testing at atmospheric pressure, where you can sort of just whip stuff together, start doing testing, you're going to want to really take a step back, draw up your system on paper, talk to your colleagues, go through and figure out if this thing was to fail, how is it going to fail? If my pump pressure just goes off and all of a sudden my pressure is at 25,000 psi or something, where is the system going to fail? And mapping out, do you have pressure relief systems in your setup? Do you have over temperature systems for shutdown? Do you have secondary confinement? In this case, this is a big acrylic box that can go over the whole setup um, to act as that secondary confinement. Um, Reducing flow rate error. So as I talked about before, this can be a big problem. There's a number of things that you can do to mitigate your flow rate error. So you can select a pump with higher precision. If you have a 250 milliliter syringe pump and you're trying to control stuff at 100 nanoliters per minute, you're probably going to get the wrong flow rate. You can always calibrate these with flow meters. However, flow meters tend to only like to work with water, or in some cases, other pure fluids. They don't work with multi-phase or with oil or other nasty things. And so you can sometimes use a flow meter to calibrate your pump, but it's difficult to run them in line with the pump. So typically you'll have to rely on the pump flow reading. You can reduce the volume of the system, which will only make things better. Control the temperature of your lines, and you can utilize on-chip measurement for extremely low flow rates. This is in our patented flowback test that this one has some audio on it.
All
It's
of our
fun.
tests are based on
Adam's in the call here, so he gets to hear his own
80
voice.
to 120 nanometers.
So what we're doing
This
here
fluid
is
actually under a microscope.
basically injecting fluid through the chip, and then to measure the flow rate back, I don't know if I can pause this.
First is a tight shell matrix with customized pore throat sizes and processes. The second is a high.
So what we're going to do here is flow fluid from the right to the left, and this flow rate's on the order of nanoliters per hour. So you'll see that we're so this here is the oil flowing back, and we're measuring the flow rate with a microscope. I'll leave this so you don't have to hear two voices at the same time. There we go.
And Tom, just on that one, so basically what we're doing is we're calculating the oil that's in those channels, and because we can measure it visually, we can see how much oil has flowed out. So that's what you mean about measuring it on the chip rather than using a measurement off chip on a flow meter.
Absolutely. If you were to measure flow rates at the nanoliters per hour range, almost for sure the microscopic leaks in your system are going to be larger than that, and you're going to get the wrong answer. So typically at larger flow rates, you can rely on the pump readouts, but once you get into that nanoliter, sub-nanoliter per minute range, it's going to be challenging unless you have a very purpose-built low flow rate system. The challenges with live sample handling are also when you're running the tests. So gas loves to just flow really easily because it has high compressibility and very low viscosity. So when you fabricate your system, if you don't take that into account and you turn on your gas bottle, you're going to shoot gas through your chip and out the other side. So just be aware that you want to make sure that you're taking this into account. And the gas related devices that we sell as a company, we incorporate this for you, and you don't have to worry about it. But if you're making your own devices, something to take into account. Also, you want to make sure that you're controlling the pressure drop across the chip accurately. And you're going to want very low pressure drop in order to make sure that gas doesn't shoot across. In order to limit the flashing of live oil, which is a big concern when you're trying to do phase behavior measurements, accurate heating and strategically placed pressure sensors along with using actuated valves to allow precision control of the fluids is a good thing to have. So at the beginning, Jason alluded to this, that unfortunately no one material is perfect. So you want to select the right material for the right process. The O-rings, chip holder, and chip are all things to be aware of. In our case here, the chips are quite compatible with fluids. Silicon and borosilicate gas chips come with the downside of being more expensive than polymers. So if you don't care about fluid compatibility, you might choose to go to a polymer system. For the actual wetted metals, stainless steel is really good for most applications, carbon dioxide, hydrogen. But you will need to switch to like a nickel superalloy if you want to use H2S or extremely saline brines at high temperature. For seals, couple of things here is that the most standard product that you're going to see out there are FKM fluoroelastomers or Viton O-rings. These are really good for most things. They're very inexpensive and very available. If you get up to a little bit, if you start using CO2 and other gases, you might find that your O-rings start to fail, and they can fail either by swelling. So in this case, I believe this O-ring was left in acetone, and the O-ring absorbs that. Same thing would happen with supercritical CO2. the O-ring expands and it'll break out of its O-ring grooves. And if you depressurize it, the O-ring will actually explode. And that's not great. So in order to avoid this, you can go to what's called an explosive decompression resistant O-ring. This is just a picture of a damaged O-ring over there.
Actually, Tom, just for
Yep.
fun, can you tell us a little like the difference in pricing typically that you find between these types of seals? Like,
Oh
you
yeah,
know,
it can be this FFKM one, which goes trade name is like Calres. It will these ones can cost over 1,000 times more than
yeah.
um the
Yeah,
cheap
basically the
ones.
FKM ones are like pennies and the other ones could be like $40 for a one seal.
Yeah, exactly.
Yeah.
And the last part that can be challenging when you're running a lot of measurements is your data pipeline. So you're going to see that you have a whole ton of sensor logs and images that you need to store on your computer. Each pressure measurement has an associated timestamp, and each temperature measurement has a timestamp. And you'll need to put all of these together into a big database or into a big Excel file, and then line up all of your images with your sensor logs. Um, this is usually done on a separate computer for image and data processing. In the case of Sapphire Lab, we've incorporated this whole pipeline into a software suite, but you can also use open source products to sort of do it at a smaller scale. And in that case, you're going to import everything, do your image analysis, get the results from that, and then line up the sensor logs in an Excel file um, in order to get a final result. The last thing here is some tips on getting good images. So I want to make sure everything's clean. This perpendicular sample tilt issue you have to be aware of. Um, if you're cooling the chip holder down, you're going to get condensation. So you're going to want to mitigate that so you don't end up with water droplets. Fluorescence imaging gives better contrast, so something to be aware of. And then um, removing vignetting, which can be a problem. You can use flat field correction to address that. And, you know, lastly, if all of this seems like a lot of work and you want to just buy something, you can just reach out to us and we can handle all this stuff for you. There's some email addresses for you, and I'm sure that you'll have those available other places too. And last two slides here before we turn over to questions is that our website now has a resources page on it, so you can go check that out. It's got lots of awesome materials for all of the tests that we've developed as a company, some of the case studies for our clients who have been using our testing and found a lot of value in the field. And then there's also some of the papers that we've published, which has been quite a lot of papers. So you can check that out if you want to see some more details on how these things actually run and some other frequently asked questions in blog posts and things. And last thing is if you're really keen on completion fluids, there's an awesome webinar that's coming up November 18th. So make sure that you come check that out and register for that on the website. I think that Alan will be sharing the link as well for that.
Great.
So,
Thanks,
Jason, I'll turn it
Tom.
over to you.
Yeah. So, Tom, thank you very much. That was excellent. And as I said before, I mean, there's a lot of components here. There's a lot of detail we could go into. So I have some questions for you. I mean, we don't really have much coming from the audience. So I just remind everyone, if you want to ask a question, put it in the chat. But for now, I've got a series of questions I'd love to ask you. So can you tell me what's a component that you think people spend too much money on when they're putting together their own system that maybe they've bought something that doesn't need the features that they're paying for? Like, is there something that people usually overspend on?
So, when people start out, usually they're just grabbing everything that they have in the lab and putting it together into a system. Um, the part that can get expensive is if you're using the most expensive seals for everything, then you're wasting money. The rest of this stuff can be repurposed, and buying an expensive pump, I'm sure you'll like it in the future. But if you're spending money on $40 O-rings and throwing them out at the end of your test, that's a good way to waste a bunch of money. Also, you just want to be aware of selecting pressure sensors that are within the right range, temperature controllers that are within the right range. Um, Temperature
Okay.
controls and pressure controllers, pressure sensors are probably also good areas to buy what you need and not the most expensive product on the market.
Okay, great. Thank you. Okay, we have a few questions from viewers here. So Martin had a question that says, great input. Thank you very much. What is a good approach or technique to gas tight the inlet outlet of glass chips as not breaking them in the process?
That's a good question. So this is a problem that is very, very common. So when we started up Interface, we adopted a chip holder that was out of the University of Toronto, and it involved putting a chip onto the system and then bolting down 4 screws in order to compress the O-rings. And if you didn't get it just right, it would break the chip. So the way that we've mitigated that with our chip holders is we've made and patented a screw top chip holder. So basically the chip will sit in there, you can screw it down, get your chip ready to go in like, 20 seconds. It's great. If you're using other products, there's adhesive ports that you can glue onto your chips to get to pressures. There's other ways to make O-rings seal onto the chips, but creating a system where you don't over tighten the manifold is a challenge and something that you'll have to sort of iterate on if you're designing your own chip holder.
Okay, great. And another few here. Enoch had a question that what is the recommended maximum length of the lines to avoid temperature influence in our flow rates?
So that is very dependent on your test. So what you're going to want to do is just measure the volume of your lines and then get a thermometer into your lab. If you have a fancy lab, you probably have less temperature change throughout the day. If you're in a more basic lab, you might have very high temperature changes throughout the day. And you can look at the thermal expansion of your fluids and multiply it by your temperature differential, and you can get your effective induced flow rate and determine if that's going to impact your test. That's basically the answer, because some of these tests are pretty resistant to flow rate change and others are extremely sensitive to it. So it depends on what you're doing.
Okay. The dreaded it depends answer. Okay.
Yeah.
Okay, thank you for the non-answer. Okay, Mohammed, thank you very much, Mohammed, for actually attending here. And Mohammed is from McMaster University, and so he's got a question. He said he has a question regarding the sample bottles when we are dealing with small fluid volumes, for example, less than 10 milliliters. What is the smallest sample bottle we can purchase?
Good question. So there exists, to my knowledge, no sample bottle that is less than 10 milliliters on the market. Unfortunately, you can find syringes that are smaller than 10 milliliters. The smallest sample bottles that are on the market are the ones that we manufacture, to my knowledge, ones that have mixing rings incorporated. Um, those ones are about 50 milliliters. The challenge with making extremely low volume ones is that they have to put mixing rings in there is challenging. Um, so if you're going to be doing stuff less than 10 milliliters, you might consider just directly using a syringe pump with your fluids.
Okay, but I guess that would only be if you're not using live fluid, right?
Yeah, you could still handle gases that way. But yeah, you would have a challenge if you're going to be using
Okay,
if you're going to be using live oil. I wouldn't say
okay.
you could use a 10 ml bottle too easily.
Tom, okay, so that was the questions so far from the audience here. Actually, Enoch had another one here just now. He said you've already mentioned some negative sides of using additional samplers. How can we quantify the impact of them in the flow rate to account for the error they may induce?
Yeah, so what you can do here is you can purchase a flow meter and hook it up downstream of the bottle, set a flow rate on one side of the bottle and see what the flow rate is on the other side. That would be probably the easiest way to do this. If
Okay.
you're The other way to avoid it is to design your experiments to be controlled on pressure drop rather than flow rate, and then you don't have to deal with that, which is what we largely do.
Okay. Now, Tom, I kind of asked you a question earlier about, the ones that components people spend too much money on. But how about what are the products like? What components out there should people never cheap out on? I think you alluded to it earlier, but like, if given the choice in a budget, where would you spend money versus one area versus another?
The There's certain spots that um, there isn't a ton of choice on. So tubing and valves, there just isn't a lot of manufacturers that supply stuff at this pressure rating. And I would say that the area where you should definitely never skimp out on is your pressure ratings. So if you're running 15,000 PSI tests, just never buy the 5,000 PSI tubing and think it'll hold. Um,
Okay.
that's probably the most fundamental one.
Okay. And actually, another one I was wondering, so you've been doing this for a lot of years, 10 plus years. What is it that you know now that you wish you could tell yourself 10 years ago when you were designing a system and trying to figure this out? Because the one thing people probably should know is that, us getting to the point where we actually have a system we can sell, it didn't happen in day one. It happened over an accumulation of 8 plus years of experience. But if you could give people an advice of something that you've learned now that it's not obvious, that it took you years to figure out, well, is there something that you could point to?
Um, the the biggest one that we've learned was around flow rate measurements and microfluidics and just how to when to trust your pump readout and when not to. That cost us a bunch of pain and suffering along the way. It can really impact the repeatability of your results if you're um, trusting that your 1 liter pump will do 100 nanoliters per minute because the display says it will. You're probably wrong, and you'll probably get bad results.
Okay. Okay, cool. And I know we're probably a little bit over time here. We're past the hour, but just wanted to ask you a few other questions. So we've talked a lot about system design and components, and obviously you've touched on the chip side of it, but obviously the chip itself is kind of the heart. I think of it as the heart of the system in the end. Like it's amazing how many components you need to get proper data and proper results and run a test successfully. But when you're looking at chip design or chip fabrication, let's call it, not the design of the channels and so on, but the fabrication process, what can you what advice can you give people on chip fabrication that might help them in their own labs or their own fab shops that they have around in their academic institutions and around the world, when things to consider or to think about when they're making chips?
I think
Assuming
that
they're making chips, say,
yeah,
similar to what we do, which is silicon
the
glass.
the probably the biggest one is to just look at the making versus buying option and realistically looking at the cost of training and growing a team to build your own chips in-house. It can be if you think that you can just send somebody to a clean room and start having workable chips the next week, you're not going to. It's definitely something you can learn, definitely something that people do all over the place, but it's definitely also a learning curve. So be aware that it takes some time to set up a process, and if you want to have something working soon, purchasing something is probably easier.
Okay. We've got two more questions here. I'm going to answer one quickly, I think. So Martin had a question that said, what silicon glass wafer thicknesses do you use for the high pressure devices? So I think if I'm, is it, it's our chips are 2.75 millimeters thick. 1 mil is the silicon, and then 1.75 is the glass. Is that
Yeah,
correct, Tom?
that's right. Yeah.
Okay, so 2.75 is the total. Again, one is the silicon. Mohammed had another question. I said, great, thanks for the answer when we were talking about the sample bottles. Is there a way to maintain the temperature throughout the system from the syringe to the chip holder? For example, when we have live oil in the sample bottles, we want the temperature to be high before the injection as well. And that's a great question. And I mean,
Yeah.
something we've put a lot of time into. So maybe you can speak to that.
Absolutely. So we've absolutely spent a lot of time on that. There's a bunch of ways that people do this. Back at University of Toronto, we did some tests where we put the tubing inside of a larger polymer liquid line and like flow a water bath at high temperature over the lines. That's not really super scalable because then you have to fit liquid cooling or heating over valves and stuff like that. Electrical is really the way to go. And if you're doing it in-house, you can purchase band heaters and rope heaters and insulation and make something work. It presents with it a lot of safety hazards if you're running at high temperatures. So I would say, once you start running stuff over 70 degrees, purchasing a professionally made heat trace system is probably a good idea unless you're going to put a lot of time into it. But
Yeah.
for our commercial systems, we heat trace in a separate heated conduit all the way from the sample bottle all the way to the chip holder. And we have a
And
separate temperature controller just for that section.
yeah. And maybe Mohammed, one of the things too, I mean, so we used to have um, specific custom made heating jackets we made for our sample containers, sample bottles, where each of them were that had the heating jacket on. And as Tom mentioned, we're heat tracing the lines as it goes to the chip holder. And then we're also heating the chip holder. And we also have heating jackets for that too. Um, Tom mentioned there about not using, like going to electrical and rather not using, like, say, heating baths. He mentioned to me the other day the reason that you don't want to use heating baths is he said if you get too high, it becomes a real safety issue having, you know, hot fluids that could spray onto people. So it becomes a problem from that point of view. Um, yeah. Uh, okay. I think that's all the questions we have for the moment. I mean, maybe Tom, just the another maybe final question I'll leave you with is like when you look what in your experience, like what's been the hardest component to source for a system and maybe why you had to build it yourself?
I would say the software has been the hardest piece to
Oh,
source.
not the chip holder, not the chip
Well, the
holder or
chip
something like
holders
that.
too, but I think that the software for logging all the data and aligning all of the data has been the biggest thing. When we started the company, it was like we were sometimes spending like 2 weeks to do some of the more complex analysis on one test, and now that same analysis can take place with 5 minutes of user work, and the rest is done automatically. I think that the software pipeline, especially if you're handling large volumes of tests, is where most of the challenge has been.
And most people don't want to know they use, say, ImageJ or something else to do the data analysis. What is the work that they're having to do before they get to that point? That might be something just to mention.
Yeah, so there's a lot of data cleanup, um, making sure that you have timestamps on all of your frames and all this stuff, and aligning your images and masking them and all this stuff that can take a lot of time just to crunch through this monotonous work that's involved around the specialty image analysis for microfluidics.
Okay, great.
Yep.
Well, Tom, that's all the questions, and I think we'll leave it there, and we look forward to trying to maybe delve into a specific topic again in the future. So thank you very much for the time and the information. I hope everyone got something valuable out of it that they can apply to their own research and their own systems. And with that, we'll leave it there.
Great. Thank
Have
you,
a great
everybody.
time. Have a great weekend. Thank you.